In the last episode, we saw that controllers, schedulers, kubelets, and users all work through the API server. That may feel indirect. Why not let each component call the component it needs directly? Direct communication looks attractive in a small system. The controller could call the scheduler could call the kubelet, and the kubelet could report directly to the controller. Each conversation appears simple on its own. Of course, Kubernetes has far more than just three components. There are users, admission controllers, autoscalers, storage and network controllers, and often hundreds of kubelets. If every component talked directly to every other component, each connection would need its own security, retry logic, version handling, and failure recovery. Very quickly, the system would become difficult to manage. But direct communication creates a more subtle problem. Each component can end up with its own version of reality. The controller may believe that 5 pods are running. The scheduler may see only 4. And one kubelet may already know that 1 pod has stopped running. So when those views disagree, which one should the system trust? Direct access also spreads risk. If every client can call every component, each component must authenticate callers, authorize actions, validate objects, enforce policy, and record an audit trail. The same safety rules are then copied across the entire control plane. The system needs a better boundary. Not one giant component that makes every decision, but one common contract through which state is read and changed. That boundary should apply validation and policy once, preserve an authoritative record, and notify interested components when state changes. Kubernetes places the API server at that boundary. Users and control plane components use the Kubernetes API. The API server validates and mediates those operations. The durable object state is stored underneath in ect. Now let's follow one example request. A user asks Kubernetes to create a deployment with 5 replicas. Before that request can become cluster state, the API server authenticates the caller, checks authorization, applies admission policy, defaults and validates the object, and then persists the accepted result. Notice what the API server did not do. It did not schedule a pod, start a container, or repair a node. It accepted a valid state change and made that change visible. Other components remain responsible for acting on the objects they understand. Once an object changes, interested components need to know. They use watches through the API server. The deployment controller watches deployments. The scheduler watches unscheduled pods, and kubelets watch pods assigned to their nodes. Each component sees the same object model but reacts in its own way. Now the indirect design becomes clear. A user writes a deployment. The deployment controller writes a replica set. The replica set controller writes pod objects. The scheduler records node assignments. Kubelets report running status. These components coordinate by changing shared objects, not by calling one another's private functions. The object model also separates intention from observation. A spec describes what someone wants. Status describes what a component has observed. Different actors can update the fields they own without sharing private memory or internal code. This controlled indirectness creates 4 major benefits. Components become loosely coupled. Security and policy are applied consistently. State changes can be audited. And new controllers can join the system by understanding the API without changing every existing component. One detail is worth making precise. The API server is the authoritative interface, but it is not the durable database by itself. Accepted Kubernetes object state is persisted in ect. The API server is the guarded path through which that state is read, changed, and watched. The architectural shift is now visible. Without a shared boundary, components exchange private messages and carry pairwise assumptions. With the Kubernetes API, components coordinate through shared objects, common policy, and well-defined state transitions. This is controlled indirectness. The extra hop is not accidental overhead. It is the mechanism that gives Kubernetes a common language, consistent guardrails, shared state, and independently evolving control loops. But centralizing coordination creates an obvious concern. If every read, write, and watch passes through the API server, does that single logical center become the bottleneck or the single point of failure?